All right, let's start by creating a database. We will use the cells database. We will show you how to create your own database, also called schema, starting from scratch. Only in this way can you grasp just how powerful SQL can be. Therefore, we will define a database and then create the other components, such as tables and fields. We will use the data definition language create statement to create a database. Quite intuitively, the command we need in this case is create database. The syntax to abide by is create database. The optional statement, if not exists, the name of the database, and finally, a semicolon. Let's break down this entire line to understand the meaning of each element. Create database will obviously create a database as an abstract unit. This means that for the moment, the database will not contain any data and will simply represent an object ready to be filled with information. Think of it as creating a canvas on which you would be able to draw your relational schemas later. If not exists, we'll verify if a database with the same name exists already. If it does, this will impede us from creating a database with the same name. The brackets around indicate that the statement between them is optional in the syntax. Optional means you could either type or omit the statement. This is the situation with if not exists. Even if you don't include it, the code will run anyway. Nevertheless, we advise you to always use it because it allows you to avoid potential errors when working with large amounts of data. It is good to build the habit of attaching this phrase straight after the create statement. Next, we will have to specify the name of the new database. We strongly suggest you give a name that is short, but at the same time, as related to the content of the data as possible. Try to avoid assigning names like database_01 or database_about_cells_in_new_york. In our case, the data we will work with is about the customer cells registered in a company. For this reason, we will call the database sales. Whether you use uppercase or lowercase letters only, or both, it's the same for SQL. The SQL code is not case sensitive, neither when assigning names of objects nor when writing queries. Otherwise, in this element, the quotes are optional. You could either say cells within quotes or without using any quotes. It makes no difference. Finally, you should always end your statements with a semicolon character. It functions as a statement terminator. Yes, it is often true that your queries will run properly without it, but this is not the point. In longer scripts, when your code contains more than a single statement, the semicolon is indispensable. So, please, try to end your statements with this character. This will not only help you avoid errors sometimes, but will also improve the readability of your code. Okay, so I guess we are ready to type down our first query and run it, aren't we? Let's type create database if not exists without brackets. Cells, keeping in mind that we are allowed to omit the quotes without any problem, and semicolon. Now, it is important to note that this entire line is nothing but a piece of text until you execute it. To execute or run a query, you must press this lightning symbol. The alternative is to implement the shortcut combination Ctrl, Shift, and Enter. So, what are we waiting for? Let's press this button and see the output of our work. At first sight, it seems nothing happened. This is not true though. When new databases, schemas, or tables are created, we always need to refresh the content in the schema section at the bottom left part of the screen by pressing this little button here. Ha! The cells database is ready for use. Great! Please remember that you could have achieved the same output if you had used create schema instead of create database. Considering that database and schema are practically synonyms, this seems like a logical alternative, right? We must always specify the type of data that will be inserted in each column of the table. Therefore, in the next lessons, we will introduce you to the various data types available in SQL. Different data types represent different types of information that can be contained in a specific column. There are a few measures that characterize a data type. First, Let's say you would like to store the surname of a person in one of the columns of a table. Therefore, to fill in the column with data, you will need letters only. The relevant text format is called string. For instance, James is a string. Length is a measure used to indicate how many symbols a certain string has. For example, the string James has a length of 5 symbols. Jackson, on the other hand, is a string that has a length of 7 symbols. Okay. Digits, symbols, or blank spaces can also be used in the string format. It is very important to note one thing, though. No mathematical operations will be executable within a string. They will only convey text information. Think of addresses. Hugh Street 45 is a string, and you cannot use 45 for addition or multiplication, for instance. Another characteristic you need to understand is size. It indicates the memory space used by a data type and is measured in bytes. You can think of a byte as the approximate space one symbol will require from your memory. So James has a length of 5 symbols and a size of 5 bytes. Finally, consider storage as the physical space in the computer drive's memory, where the data is being saved or stored. Hence, quite often, you could hear phrases like, "This data value occupies 50 bytes storage space," or "This variable takes 10 bytes of storage." We said the text format in SQL is called string. For instance, James will be treated by Workbench as a variable of the string data type. Please remember that data formats dealing with information of this type are also called alphanumeric data types. So please don't be surprised if you hear this name quite often. There are a few string data types in SQL. They are quite similar, with the main difference being the storage required to save them. One of these string data types is the character type. The keyword you must use is char, pronounced char. It is a string type that demands fixed storage regardless of the length of the value you are assigning to it. An example will better clarify the concept. Let's assume you have set char with 5 in parentheses. The number 5 represents the maximum number of symbols you are allowed to use in writing a value in this format. Therefore, this column, the name James, which consists of 5 symbols, will require storage of 5 bytes. If instead you type Bob, the length will be 3 symbols, but the storage will still be 5 bytes. Now you see why char is referred to as a fixed storage data type, right? Another frequently employed string data type is varchar. Its name derives from variable character. The variable part regards the storage space needed. Unlike char, varchar will respond to a change in the length of the string that has been inserted. Hence, if varchar is with a maximum of 5 symbols and you enter James, 5 bits of storage will be taken. If you type Bob, 3 bytes, not 5, will be required. In other words, in the parentheses, you indicate the maximum storage a varchar can occupy. Such maximum storage could decrease. It is not fixed, as is the case with the char type. A further distinction between the two formats is the maximum size SQL allows for a char and a varchar type. The former cannot be assigned a limit higher than 255 bytes, while the latter can store much longer strings, up to a maximum of 65,535 bytes. You're probably wondering why char exists, considering the fact that varchar is a lot more responsive to the data value inserted. Also, varchar would require smaller storage if the value inserted is shorter than the defined maximum size. The reason is strictly technical, and it concerns mainly advanced users. When processing data, char is about 50% faster than varchar. In our course, this contrast in speed will be of no significance. But when professionals must deal with huge amounts of data, such a difference can become important. Let's look at another example that illustrates a practical application of the two data types. Imagine we would like to add company acronyms in our company's table from the sales database. Each of them will be composed of exactly 3 letters. In this situation, char would do a great job, as it would provide a well-organized column that would process the data efficiently. Alternatively, think of a situation in which you have to store people's passwords. You tell them the password can be composed of any kind of symbol, digits, letters, or others, but the symbols cannot be more than 10 characters. Varchar with a maximum of 10 symbols would do a great job, because a 5-symbol pass, for instance, will not occupy storage for a value that is twice as long. Awesome! This is all we are going to say about char and varchar at the moment. There is another alphanumeric data type we would like to introduce to you. Its name is enum, derived from enumerate. It is particularly handy when you know in advance what type of columns you will be working with. For example, if in a certain column you want to insert the gender of a person, you should specify the possible values of M and F. Then, MySQL will show an error if you attempt to insert any value different from M or F. This string data format is not used as frequently as the previous two, but sometimes you will really love the fact that it is there and can be applied readily. Great! These were the most frequently used string data types in MySQL: char, varchar, and enum. Often, you will need to use a data type that allows you to store numbers. Numbers are stored in so-called numeric data types. We will go through the types that are most notable: integer, fixed point, and floating point data types. In this lesson, we will focus on integers. They are whole numbers with no decimal point. Numbers like 5, 15, minus 200, and 1000, for instance. The integer, or int, allows us to insert integers into tables. There are a few subcategories of data type, and they are provided in the table you see here. For example, the tinyInt type occupies merely a byte of memory and can contain values between -128 and 127. Hence, tinyInt gives you the chance to designate values between -128 and +127. 256 different values in total. Don't forget the 0. To understand why each subtype has 2 ways of representation, we must explain the difference between signed and unsigned values. This is more intuitive than you might think. If the encompassed range includes both positive and negative values, the latter, of course, being signed with a minus, we are in the signed form of representation. In other words, in the tinyInt case, signed refers to the range between -128 and 127, both included. If we allow integers to be only positive, logically, we will need no sign in the representation of the range of 256 values, hence the label unsigned. For tinyInt, this regards storing values from 0 to 255, both included. We must mention one last thing regarding this topic. Remember, integer data types are signed by default. Put differently, SQL assumes you would refer to the upper representation of the given type, the one including both positive and negative values in the range. If you want to use a range containing only positive unsigned values, you would have to specify this in your query. We will see a relevant practical example later in the course. Okay, continuing further, the next data type we'll consider is small int. It is related to a storage size of 2 bytes and values belonging to the range of -32,768 to +32,767, both included. This is the range when small int is signed. If unsigned, the interval will be from 0 to 65,535. This way, you can read the rest of the table and see the ranges associated with medium int, and big int formats. Now, you are probably asking yourself, why not just use big int all the time? It is the largest interval available for integers, so why bother with smaller integer data type formats? The answer comes with the idea of improving efficiency in terms of computer processing speed. if you are sure that in a certain column you won't need an integer smaller than 0 or greater than 100. For instance, when you are registering the scores of a test, tinyInt would do the job perfectly, and you would not need more storage space per data point. Thus, depending on the data that will be inserted in a certain column, a smaller integer type may suffice and increase the processing speed. Precision refers to the number of digits in a number. For instance, we say that the number 10.523 has a precision of 5. The other term, scale, refers to the number of digits to the right of the decimal point in a number. Therefore, this same number, 10.523, has a scale of 3. Okay. Often you will see a data type succeeded by a pair of numbers within parentheses. The first one indicates the precision of the number, and the second one its scale. Therefore, a data type of 5 and 3 will be related to such numbers as, for instance, 10.523 and 36.875. Great! The next important distinction to remember is the one between fixed and floating point data types. Fixed point data represent exact values. Decimal is a good example of this type. Decimal 5 and 3 will contain a value with a total of 5 digits, 3 of which will be after the decimal point. Again, 10.523 would fit. Perfect! Here is something interesting. Should you insert only 10.5, SQL will fill up the number with zeros, so 10.5 would automatically become 10.500. However, if you insert a number with a larger precision, such as 10.5236789, SQL will round this number to a value that complies with the indicated structure, 10.524. And you will see a warning. This is just the way SQL behaves. Okay? Good. Furthermore, when only one digit is specified within the parentheses, it will be treated as the precision of the data type. Writing decimal of 7 would be the same as writing decimal of 7 and 0. Hence, a decimal of 7 or a decimal of 7 and 0 will require an integer written with at most 7 digits, right? For example, the number 1, 2, 3, 4, 5, 6, 7 fits the criteria. Perfect! We shouldn't forget to mention that decimal has a synonymous data type. It is called numeric. Please do not confuse it with the entire set of numeric data types. Integer, decimal, numeric, and the floating point ones you will see in a minute. These are all numeric data types, but this is a specific one. Numeric functions in the same way as decimal and is a fixed point data type. This configuration may sound a bit strange, but this is simply how it is, so we'd better get used to it. Okay? Very good. Numeric and decimal are great for representing a currency. For example, the salaries in a company could be represented by a 7-digit number with only 2 digits after the decimal point, indicating dollar cents. This is the perfect moment to abide by the following syntax. Numeric, P, S in parentheses. P stands for precision, the number of digits of any of the values, in our case 7, and S stands for scale, the number of digits after the decimal point. Thus, a salary of $75,000.50 will fit this numeric data type. Awesome! The other important type is the floating point. It is used for approximate values only and aims to balance between range and precision, hence the first part of its name, floating. Unlike the fixed point data type, when one is working with the floating point type for the precision of 5 and scale of 3, the insertion of the same number, 10.5236789, will not give us a warning. Instead, the number will be rounded to a new one with only 3 digits after the decimal point. That is, SQL will store this data as 10.524, which is an approximate value. So, the main difference between the fixed and floating type is in the way the value is represented in the memory of the computer, as either a fixed point type or a floating point type. In addition, the former will provide a warning whenever its structure is not respected, while the latter won't. Lovely. Float and double are floating data types. The difference between the two lies in the capability of storing data within a memory storage limit, and, of course, this distinction is purely technical. Float needs 4 bytes of memory to be stored. In SQL, this is referred to as single precision. As many as 23 digits can be used to represent a value of the float type. Double is a data type that needs twice the number of bytes, 8. It represents double precision values. A data point of the double type consists of a maximum of 53 digits. Great! Quite intuitively, date is used to represent a date in the format year, month, day, using 4, 2, and 2 digits respectively. Time is not part of this representation, hence the range of date is huge. It is between the 1st of January 1000 and the 31st of December 9999. It seems that this data type is eternal, doesn't it? For example, we could store the 20th of July 2018 in the date format, and it would look like this, 2018, 0725. If storing the date in a record does not suffice and we must store time as well, we could use date time. Next to the date, we could save the time, shown in the following format, hours, minutes, and seconds. We can even have fractional seconds, parting up to microseconds with 6-digit precision. The range of this data type is one like that of date, with the difference being that the hours can go from 0 to 23 hours 59 minutes 59 seconds and 6 times 9 microseconds. An example of data value of this type would be the 25th of July 2018, 9:30 in the morning. Great! These data types refer to date and time precisely. That is, you can think of date time as representing the date shown on the calendar and the time shown on the clock. The following type, timestamp, is used quite frequently for a well-defined exact point in time. At first sight, this distinction seems vague, I guess, but in a couple of minutes, you will understand what it is about. Primarily, the range of timestamp is much lower, from the 1st of January 1970 to the 19th of January 2038, 3:14 and 7 seconds in the morning, Coordinated Universal Time, UTC for brief. This shorter span immediately tells us that timestamp will not be the preferred option for storing birth dates and times, as date and date time appear to be the better option. What is the advantage of using it then? Well, timestamp records the moment in time as the number of seconds passed after the 1st of January 1970, 0 o'clock in the morning. So, for instance, the 25th of July 2018 will be equal to more than 48 years, or 1,535,155,200 seconds, to be precise. Wow! What does that trick allow us to do? Professionals would love to discuss storage space and processing speed differences between timestamp and date time, but I suggest you remember the following. First, representing a moment in time as a number allows you to easily obtain the difference between two timestamp values. So, for instance, if you know that the start time of an event is the 25th of July, 9 o'clock in the morning, and that the end time is the same day, 10:30, and if you have stored both moments in timestamp, you can subtract the first value out of the second value and obtain the duration of the event. 1.5 hours expressed as number of seconds, 5,400. The second advantage stems from the first one. Timestamp is appropriate if you need to handle time zones, something date time is not capable of doing. For someone in the UK, something might have happened an hour or 3,600 seconds after the 1st of January 1970, while in Paris, the same event would have happened 1 hour later, at 2 in the morning, as there is a 1-hour time difference. However, the latter need not be stored as 2 hours away from the 1st of January. It would still be recorded as 1 hour after the 1st of January 1970, 0 in the morning. And your computer would handle the time zone difference itself. Therefore, please remember that with such string types as char and varchar, as well as with all date and time types, data in SQL must be written within quotes, allowing it to properly process the respective values. Only numeric values are written without quotes. Another useful data type we'll cover in this lesson bears the name blob. It is derived from binary large object, referring to a file of binary data. Data with ones and zeros stored as a single entity in a relational database management system. Put simply, this data type involves saving files in a record, as opposed to saving data values. Typical file formats that fall under the blob category are doc, XLSX, XML, JPEG, media files, and more. To visualize the idea, think of our customers table. Imagine that people were providing photos as well. If we added a blob column to this table, we would be able to store the JPEG files with the photos in it, and refer to these files according to their customer ID, for instance. Awesome! Remember all these string, numeric, and time data types because they are relevant for more than MySQL. Structured in the same or a similar manner, these data types can be found in every existing relational database, as well as in other SQL supporting software like PostgreSQL or Microsoft SQL. In addition, similar types of data are valid when one is working with programming languages like Java, C++, Python, R, and so on. This will do for now. In SQL, creating a table is much like creating a database, with one substantial difference. To create a database, we must type create database, preferably, if not exists, the name of the database, cells, and then semicolon. When creating a table again, the DDL's create statement is needed to say create table. It must be followed by the table's name. But before the statement terminator, we must open and close parentheses. Within them, we will place the column names belonging to this table. This is the substantial difference I just mentioned. Another compulsory requirement is to add at least one column. Otherwise, SQL will display an error. This makes sense because there is no point in creating a table that does not contain a single column, right? Where would we store the data? Okay, so here's the syntax we must follow when creating a table. Create table, table name, open parentheses, column 1, data type of column 1, constraints on column 1, comma, then the name of column 2, its data type, and the constraints on it, comma, and so on and so forth until you finish the columns that will be contained in this table. At the end, instead of inserting a comma, you must close the parentheses and terminate by placing a semicolon. All right? Fantastic! Let's clarify this concept through an example in our cells database. Let's look at the relational schema and focus on the cells table. We will need to set up 4 fields, right? A purchase number, a date of the purchase, a customer ID, and an item's code. Cool. Let's begin. All right, create table cells and open parentheses. For better organization of the code that follows, I suggest you start every column in a new line. So, column 1's name is purchase_number. It is of the integer type, and it should be different than 0. As we said in the earlier lectures, it will be our primary key. Cool! There's an interesting extra constraint we can add to this field. It is called auto increment. It frees you from having to insert all purchase numbers manually through the insert command at a later stage. It assigns the number 1 to the first record of the table and automatically increments by 1 for every subsequent row. That is, starting from 1, the next records in this field will be 2, 3, 4, and so on until the last nth record. This feature is designed specifically for cases like the one we have here, when we need to use different numbers in every row in order to provide unique data values that can identify the different rows in our table. Great! Now, let's insert a comma and see the next column we need to create. It is date of purchase. It is obligatory to determine the corresponding data type, date. Assuming we have the requirement to register no purchase unless we also register the day on which they were executed, we'll have to constrain this field to be not null as well. Okay. As you can see from the relational schema, the remaining two fields, customer ID and item code, will make the connection with the customers and the items tables respectively. While customer ID could be null because we may register a cell without really knowing who the purchaser was, item code must be not null because we will surely know what we have sold, right? Customer ID won't contain anything but numbers, therefore int will do the job okay. Comma, and then item code. Varchar with 10 in parentheses, as we assume it will be impossible to have an item code longer than 10 symbols, not null, close parentheses, a semicolon, and when we press the little lightning button, we will run the code and be able to create a table. When you expand the sales database and then the table subsection on the left part of the workbench, you'll see that a table with the name Sales has appeared. Awesome! A few lectures ago, after we created the sales database, we said that you must execute use sales semicolon to indicate that you want your queries to be applied to this database. And that's all right. But what are queries used for? How can they help us? One of their main features is to manipulate data within a database. As you already know, data is usually subdivided into tables, and each table contains a certain number of fields. Therefore, when you want to implement various operations specifically to just one table or to a column of that table, you must write that in code, which represents writing a query. Whenever you would like to refer to an SQL object in your queries, you must specify the database in which it is applied. An example of an SQL object you already know about is the SQL table. But later in the course, you will see other instances of SQL objects, such as views, stored procedures, and functions. Okay, there are two ways to communicate this to SQL. The first way is to set a default database, just as we did with the sales database. Doing so means you will be working with SQL objects that belong to this database. For instance, the customers table or another SQL object can be referred to simply by mentioning their name in the query. The second way does not require you to have a default database. The syntax to call a table from a certain database, in other words, to use the information from a specific table, is the following. Name of the database object, dot, name of the SQL object. In computing terms, the dot is called dot operator. It signals the existence of a connection between the two object types. As an example, if you would like to operate with the customer's table from the sales database, you must refer to it in your query by typing sales.customers, and then continuing with the rest of the code. Both alternatives are frequently applied and used. It is very important to know how to refer to an SQL object in your queries.